Hello, everyone. I'm pleased today, really quite pleased, to have Dr. Lawrence Krauss with me. He is an internationally known theoretical physicist, and I've wanted to talk to an internationally known theoretical physicist for about 30 years, whose research is focused on the interface between elementary particle physics and cosmology, including the fundamental structure of matter and the evolution of the universe. Among his numerous important and interesting scientific contributions was his 1995 proposal that most of the energy of the universe resided in empty space. During his career, Professor Krauss has held endowed professorships and distinguished research appointments at major institutions all over the world, including Harvard, Yale, and CERN. He is the author of 500 publications and 11 popular books, including the international bestsellers, The Physics of Star Trek, and A Universe from Nothing. His most recent book, The Physics of Climate Change, was released in February of this year, 2021. He won a major award from all three of the U.S. National Physics Societies, as well as the 2012 Public Service Award from the National Science Board for his contributions to the public understanding of science. He currently serves as president of the Origins Project Foundation, which celebrates science and culture by connecting scientists, artists, writers, and celebrities with the public through special events, online discussions, and unique travel opportunities. The foundation produces the Origins podcast, featuring dialogues with some of the most interesting people in the world, discussing issues that address the global challenges of the 21st century. Thank you very much for agreeing to talk to me today.
It's great to be with you virtually, Jordan.
Okay, so I have a question, and I'm going to jump right into it. I wrote a paper with a couple of my students. I was the final author on the paper. We tried to relate the experience of anxiety to a physical property, to entropy, which I suppose might be well defined as a physical property. And the idea was, and you tell me what you think of this as a physicist, if you would.
Okay.
The idea was that human beings are always trying to calculate a path from one point to another. And the length of the path is going to be proportionate in some sense to the energy used to undertake the task. Okay. Right? The longer the path, the more energy. Now, we generally take a path to something that we regard as valuable, and sources of energy, for example, are extremely valuable to us. And so that might be a shortcut to doing some work because that's translatable into goods. Anyways, the cost of the voyage is an important consideration. Sure. And so whenever uncertainty is added to a plan, it becomes more and more difficult to formulate a map that lays out the trajectory appropriately. And you need a marker for that, a psychological marker. And so we assume that as the certainty of the path that you're going to take according to, given a particular reward, as the uncertainty of that increased, you experience this unease. And the unease was a marker of the increased complexity. And that would be the increased entropy in some sense of either of the landscape or of your representation of the landscape, or maybe of the disjunction between the two. So the first question I would have is, I guess, first of all, was that a comprehensible explanation? And second of all, is that a reasonable way of construing entropy?
Well, yeah, okay. The answer is it's not unreasonable in a general sense. I'm very wary. I remember, when I was a kid, actually in Canada, and I remember I was always interested in science, but in university I took sociology. And I remember becoming fascinated at the time by various sociologists' attempts to define concepts, as if borrow from physics to define concepts. And I thought, wow, this is fascinating. As I got to know more physics, I became more wary of that application, because certain things that are well-defined and appropriate in physical contexts become less well-defined and perhaps have less utility. They sound good in a social science paper, but whether they actually allow predictive value is the important question.
Right. And so that's exactly why I'm asking the question, is because I'm aware of that problem, and I wanted to see if there's some bedrock there.
Well, I think that I think you've got something in a sense that in physics, actually, in different contexts, there's trade-offs between energy and entropy, and different and they're well-defined thermodynamic quantities that are defined depending upon what you hold fixed and what you don't, and how the system evolves whether it evolved to a situation of least energy or least what's called free energy, which depends on, or enthalpy, which includes that entropy aspect, depends upon the specific circumstances of the physical situation. But that the complexity of a path is related to the entropy that is appropriate, because entropy really describes, and maybe it's probably useful for your listeners who may not be as aware of entropy as you are, that what it really describes is a macroscopic system has many different internal states it can be in. And entropy really just describes how many internal states a system has for a given macroscopic configuration of say, temperature and overall energy. A single particle in a box may have a restricted configuration, but the atoms in my body and your body can be in very many different configurations and still be at the same temperature. So there's a lot of entropy associated with a macroscopic object. And the more, if you wish, the more internal possibilities that a system has to explore within the confines of some external parameter that's restricting it, like the total energy of the system, or its heat content, or some other aspect, or its volume, the more internal configurations the system has to explore, the bigger its entropy.
So, okay, so I was thinking, for example, I'll give you a narrative example. It's actually apropos because my car did break down today. But when you're in your car and you're driving along and everything is going according to your desires and expectations, then you're generally in a low anxiety state. But then imagine that the car emits an unexpected noise and starts to buck. Now, one of the things I've proposed is that at that point, you're actually no longer in a car. And that's why you get upset, because the car is actually functionally described as a category. The car is something that gets you from point A to B. And as long as it's performing that function, then that category, which is a very low resolution category, that category suffices. But as soon as something goes wrong, same thing happens when your computer does something you don't want it to. There's so many different states that thing could be in, that your body signals that emergent complexity, and it signals the fact that you can no longer compute the cost of being where you are. And, there's fantasies that are associated with that seem like attempts to map it, right? This could be wrong. This could be wrong. I might go to a crooked mechanic. I might get ripped off. I might not be able to fix this car. Maybe I can't afford it. I won't get to work. Like the whole panoply of possibility expands very, very suddenly. And that produces an intense physiological response, which it should do. I mean, we should have physiological responses to fundamental physical realities.
We should. Most of us ignore them. And I think that's the point. The physiological response you're talking about is real. But in fact, when the car is operating well, all of those possibilities also exist. You just block them out of your mind. I mean, because
right. Well, that's an interesting thing too, right? But it's appropriate in some sense. We were trying to understand to some degree the conditions under which it's appropriate to block them out of your mind. And it's something like, as long as your predictions, but they're based on your desires, but we won't get into that. As long as your predictions match the ongoing flow of events, then you can take all of the presuppositions that order things for granted. I mean, I agree with you completely that all those things could be going wrong at any time. The same is true of the complexity of your body, right? Sure. I mean, it isn't necessarily the case that just because you feel good right now, you're going to feel good the next moment. And there's an endless number of things that can go wrong, but it's also not helpful to be aware of all of those possibilities if they're not likely to happen. So it isn't exactly that you ignore them. It's that you assume their functional significance is zero as long as your plan is operative. And
yeah, but I think, it goes back to maybe human reason being the slave of passion. I think the point is you're right. It's not worthwhile assuming all the negative things that can happen. If it did, you wouldn't do anything, right? If you want to take any action, if you assume all the negative things that could result from it, you probably wouldn't act at all. One of the things that I think we do, and one of the problems we have as a society, in fact, it's related to even my last book, is that we tend, one of the things that science does, which I think is so useful, is it quantifies uncertainty. Uncertainty is a central part of science, and too often, journalists and other people talk about uncertainty as if it's a bad thing. In science, it's actually a very good thing, because we can say, we can we can quantitatively say how accurate our result is, or how likely or unlikely a bunch of possibilities are. I think psychologically,
and that, I would say, that's an anxiety reduction phenomena. I mean, when you enter into a contract, you're doing that with someone too, because what you're saying is, well, I could be any number of possibilities, but contractually, I'll limit myself to this manifestation, and that can make you calm, and it can make us able to cooperate. And so I think that it's not only a scientific theory that provides that function. Science would be a subset of practical theory, and practical theories, they're very useful exactly for that reason.
They are, but I personally think more people I think it would be it would help people if they accepted the existence of uncertainty in a more open way. I think people are afraid of uncertainty, and I think if we, including death and the universe and all sorts of other things we may talk about, and I think accepting it as a realistic likelihood is a healthy thing, because again, it relates to some extent to some of the, I think, social problems that are happening now of kids being coddled. If you accept that bad things can happen, then when you do it's part of living, then you won't be so anxious when they do, I think. I mean, you won't be so fearful of that possibility. Okay, yeah, your car can break down, but the world isn't over. There's a whole series of other activities you can take place that will allow the world to go on, that will allow you to continue to function. But recognizing at some level a spectrum of possibilities in advance, in my opinion, and I'm not a psychologist, but in my opinion, certainly personally, I find it psychologically helpful.
Well, it is definitely the case that that's promoted among psychologists. I mean, behavioral psychologists. You may imagine that one thing you want is a theoretical configuration that encapsulates uncertainty. That's a belief system, let's say, and you measure it by its functional utility. Does it allow you to acquire what you desire when you act it out? But you need a codicil along with that, which is, well, what do you do when your theory goes wrong? And one of the answers that's been provided to that question from the behavioral perspective, it's coded in narrative as well, though, is approach uncertainty voluntarily and cautiously. Don't avoid it. And that triggers another mechanism, which is the capacity to explore, to generate new theories, to select among them, especially in collaboration with other people, and to regenerate your pre-existing models. So you need the model, and you need a system for updating the model. And you see that expressed in pretty formally in science, in the scientific technique.
Oh, it's a central part of the scientific method. And I would also argue in business and many other areas of human activity that people don't realize. What I try and convince people of, they don't realize is scientists actually really like to be wrong. At least, and whether personally they do is a different question. But the process of science, it's exciting to be wrong because it means there's more to learn, first of all.
And it might mean you discovered something.
It often means you've discovered something. And one of the things, I was chairman of a physics department for a long time, and then we started a program, a master's degree in physics entrepreneurship, which the business school dean said was an oxymoron, but I don't think so, because I think scientists and business people are very similar, because often what I realize we don't do well enough for children, for students or whatever, is teach them how to fail effectively. We give them problem sets that they're guaranteed, that have direct answers and they can get the correct answer. We even give them PhDs where they're more or less guaranteed to at least come to some conclusion. But in the real world of research and business and many other things, you may find that you have to learn how, well, the question I was asking was really not a good question. How can I use what I've already accumulated to nevertheless provide me something useful? Maybe ask a different question and go around. And so I think the training to fail effectively, namely to find that the thing you were trying to show is wrong, but nevertheless, the process by which you discover that is very useful and can be useful somewhere else is a central part of science. But I actually think it's probably very useful again in real life. And I think most business people, when I learned about entrepreneurs, I asked the physicists who become entrepreneurs what they hadn't learned, and it was just that, how to fail effectively. Because often startups, well-known entrepreneurs have had 3 or 4 or 5 startups that have failed before they get to where they're going. And I think, but it's the same of any researcher. In your research, I'm sure, as in mine, there have been many false starts, many roadblocks, many times when you just discover, hey, this problem is really not amenable to being solved, but maybe I can ask a slightly different question. So I think being aware, being less anxious of the fact that your planned trajectory is not going to go where you took it is actually a wonderful part of life. As a scientist, I often say when I write, you probably had this problem too. You write grant proposals and you write some fiction of what you're going to be studying in 3 years. And I always say that if I'm really doing what I thought I was going to be doing in 3 years, it's pretty boring, because what I really hope will happen is I'll be looking at something completely different, because some new discovery will have come up either from the outside world of experiment or from something I'm doing.
Well, is it reasonable to ask you, can you remember times when that specifically happened in your career, where you had to reconfigure and you discovered something that was worthwhile as a consequence of it?
Oh yeah, it's hard to imagine when it hasn't happened in some sense. I think let me give you an example. The one you mentioned, the discovery that the energy of empty space is the dominant energy of the universe. I was studying cosmology, and of course, and the amazing thing about cosmology is it's over the last 30 years turned from, or 40 years, from an art to a science. I think people used to say cosmologists were never right but never in doubt, but wonderfully, what's happened, because science is an empirical discipline, is that whole new data sets were coming on, new machines and new telescopes, which were allowing you to make precision tests of the universe and therefore derive models that could be disproved, which is really the central part of science. And when I was trying to understand, and I've been working on the subject called dark matter for many years, how to detect it, the fact that most of the mass in our galaxy and all galaxies appears to not shine. And now we're reasonably certain it's made of some elementary particle that's different than the particles that make you and I up. It's a fascinating thing, and I've spent a lot of my career thinking about it. But one of the reasons we became confident that that was the case, that these particles, this dark matter was not made of protons and neutrons and the same stuff as you and I, was because we built cosmological models, and we found that if this dark matter was just snowballs or something that you couldn't see, then plugging them into our models, you couldn't get a universe that looked like what we look like today, starting from a hot Big Bang. You couldn't form galaxies. There wasn't enough time. And so dark matter, it turns out if dark matter doesn't interact with light, it's easier for it to collapse early on in the history of the universe, and that gives a jump start to galaxies and et cetera, et cetera, et cetera. So we're trying to come up with a model that really was in agreement with observation. The problem was the observations ultimately weren't in agreement with that model. And so the question then becomes, what do you do? And so I was reasonably convinced at the time that the reason that was the case, that some of the observations are wrong, which is also something very important to realize in science, is that if there are many different observations, likely some of them are wrong. And again, too often journalists don't hit on that fact. They concentrate on this one exciting observation, which is likely to be wrong. And when it's later on shown to be wrong, they never report on it. And that's part of the problem. But so I basically was convinced that some of these key observations were wrong because they're very difficult. And so somewhat heretically, I made this proposal. There was a colleague of mine at University of Chicago, and I spent a year or two looking at all the data and saying, how could it be consistent with dark matter and what would be required? And the answer was, if none of the observations are wrong, then it looked to me at the time, like you'd have to have most of the energy in the universe reside in literally nothing, because observations weren't consistent with the picture otherwise. And I was convinced at the time that the reason I was doing that was so that people could focus on which observations were wrong. Mm-hmm. And so they could see that, because the proposition was so ridiculous that empty space actually weighs something. You get rid of all the particles and radiation, everything that's there, and yet empty space weighs something. That seems so crazy that surely it's wrong. And there must be something else.
Yeah, well, it seems to violate the very presupposition that enables us to identify mass. I mean, mass by definition appears to be something.
Well, mass is different than energy, okay? And energy, and if you put energy in empty space, and Einstein realized this, if you put energy in empty space, it behaves very differently than it does if you put energy in matter, like particles. In fact, what general relativity tells us is that mass isn't the key part that produces gravity, it's energy. So there's this relationship between energy and gravity. And energy in different forms produces different types of gravitational attraction. And in fact, that's relevant to the history of the universe. Early on in the history of the universe, most of the energy in the universe resided in radiation, hot stuff like particles of light moving at the speed of light. They gravitate very differently than if most of the energy in the universe resides in planets or galaxies, matter that's staying still. And so the expansion of the universe, which is gravity's response to the presence of energy, is different early on in the history of the universe when it's dominated by radiation.
Is that one of the things that contributes to the rapid inflation at the beginning?
Well, in fact, it's not quite. You're almost there. It turns out rapid inflation happens if at very early times in the history of the universe, empty space gets energy. Because it turns out if for some reason empty space gets stuck, and somehow it possesses energy, even if in the case of inflation, eventually it's going to release it in a hot Big Bang. If that energy gets stuck in empty space carries with it this property we call energy. That energy is gravitationally repulsive, not attractive. That's the key difference between energy when you put it in matter and when you put it in nothing.
Okay, so you said a couple of things that I want to follow up on.
Okay, sure.
And maybe you can take us back. So you said in the last 25 years that cosmology has transformed itself from an art to a science. And so maybe you could tell us the science. Let's go back to the beginning.
That's sure. Okay.
14 billion years and walk through it. And because I'm sure that, well, I certainly don't understand the role of dark matter or anything about dark matter. And I kind of had some sense of what the current cosmological theories were 20 years ago, but I really don't know what they are now. So let's go back 14 billion years and start at the beginning, if you don't mind.
Sure, we'll try and spend less than 14 billion years in describing it. But okay, by the way, before we get there, let me just end the last story by saying we made this crazy proposal because we were sure the experiments were wrong. It turned out the experiments were right and the craziness was true. And no one was more surprised by it than me, that this proposal that the energy of empty space it dominates the energy of the universe was right. It was just incredibly surprising. It was so surprising that eventually the observers who confirmed that fact won the Nobel Prize 11 years later.
Well, in your book, The Greatest Story Ever Told So Far, you document a large number of cases where theoretical physicists were driven to posit something they regarded as completely absurd because it seemed to fit the data, assuming that something was wrong and were later shown to be right, even though they wouldn't necessarily accept that themselves.
Yeah, exactly. In fact, one of the founders of quantum mechanics, Dirac, who was a very interesting man psychologically, among other things, once said his equation was smarter than he was because he developed this equation and it predicted this new particle in nature, antimatter, and he didn't believe it. And he said it was the equation, and it turned out to be true. But anyway, let's go back to the beginning, and when we go back to the beginning, this is an important difference between, in my mind, science and say religion. When I go back to the beginning, I go back to as far as I can extrapolate my understanding of the laws of physics back. Before that, almost anything goes. And science, we can make, and part of my job as a theoretical physicist was make speculations, but to recognize that they were just that and look for signatures that might suggest whether those speculations were right or wrong. So, for example, I actually wrote a book called Atom, which takes you back for an individual oxygen atom, from the beginning of the universe to the end, one that's in a glass of water that you're drinking right now or during this podcast. And I took it back to not t equals 0, because literally we don't know what happened at t equals 0, because the laws of physics, as we understand them, break down. Because the universe, if we extrapolate it back, our universe becomes infinitely dense, and that seems crazy, and the laws of gravity don't work with quantum mechanics, so we really can talk a lot about it, but it's not more than talk, in my opinion, right now. But very shortly thereafter, after that time, there's no reason to suspect that the current laws of physics don't describe what happened in the history of the universe. And again,
so as soon as it comes into being, the laws come into being as well.
Yeah, well, in fact, in the universe or nothing, I suggested that's certainly a possibility. Maybe they pre-existed, maybe they don't. Those are metaphysical questions. But what I did show in that book, which is fascinating to me, and the fact that 30 years ago we wouldn't have even been able to ask the question, much less answer it, is that it's quite likely that our universe could and did spontaneously arise out of nothing, no space, no time, and maybe no laws. And if you ask what would be the properties of a universe today, 14 billion years later, that arose from nothing spontaneously without any supernatural shenanigans, the properties of that universe would be precisely the properties of the universe we observe. Now, that doesn't prove that's the case. That just makes it plausible. But to me, that's a fascinating thing. And again, 30 years ago, we didn't have the tools to even, in some sense, ask that question. But we're
still estimating the birth of about 14 billion years ago.
13.8. Yeah. Now, if you actually look at the numbers, which we can measure, we now know that number, 13.8, to an accuracy of, plus or minus of maybe 100 million years or two. 13.75, I think, is the most recent number. And it's amazing. The fact that you can get beyond one decimal place in cosmology is just remarkable. And it really is a testament to the developments. When I was even a young assistant professor at Yale, I remember talking to an older colleague who said that nature would always conspire so that we could never measure the fundamental quantities of the universe better than within a factor of 2. Because that had always been the case up to that point. Every time someone claimed to have a better measurement, you'd go out and look at astrophysical uncertainties and realize it was wrong. And now we're talking about measuring things to 4 or 5 or 6 decimal places. It's really a transformation, and one we're celebrating, which is what I tried to do in that book. But the early picture, that the fact that we evolved from a Big Bang is not in dispute. Let me make that clear. The Big Bang happened just like evolution happened, and the Earth is round, and all the other things we know. There's no doubt that that the early history of the universe was a hot Big Bang. Now, and in fact, everything we now see, all the galaxies we now see and all the particles in those galaxies, the 100 billion stars in each galaxy, the 100 billion galaxies, all of that material was contained in a region smaller than the size of a single atom. And that's just
so. Okay, let me ask you a question about that.
Sure.
I mean, is it reasonable to conceptualize something like that as having a size? Because we're considering size within the universe. And it's almost, when you say that the universe at the beginning had a size, it's like it was an object in a universe that had a size. But
it's a really good question, and I should be clearer in my language. The universe could be infinite. I want to ask, as a physicist, and Wheeler would have liked this, Einstein certainly did, operational questions. I don't know how big the universe is, whether it's infinite or not, but what I do know is, how big is the visible universe? So if I ask you, how big was the region which now comprises the visible universe today at an earlier time, that has a good, that's well defined. That region the size of an atom could have existed in a universe which was infinite even then. It could have been an infinitely dense universe that was infinitely big, okay? So all we can ask, and this is really a big change also from when I was a student, because we used to, when I was a kid or when I was even a student, we talk about universe, and universe would mean everything, a kind of ill-defined quantity, everything. What the heck is everything? Now we're much more well-defined. We say our universe, a good definition of our universe is that region with which we could have interacted in the past and with which we will be able to interact into the future, even if the future is infinitely long. And that may not be everything. Right? That could be just a small region of a much bigger thing, which we now call a multiverse. So it's reasonable to describe our universe as that region into which we could have had causal contact, namely which cause could have produced effect, right? And if there's any region outside of it which we can never affect or be affected by, that might as well not be considered part of our universe,
that
right?
Distance, that causally interactable distance, that's defined or limited by the speed of light?
The speed of light and the age of the universe. Right. So, for example, in the early history of the universe, that's called the horizon. In analogy with the Earth, when you look out at the Earth, you can, when it curves, you can only see out to a certain distance. And we call the causal horizon that region with which light could have traveled to interact with us since the beginning of time.
Right.
And
obviously that's the universe as far as we're concerned, because nothing outside of that can affect us in any way.
Exactly. So operationally, it's a much better definition of a universe to be that which we can be causally affected by. And so, and because that changes with time, that's what is our observable universe changes with time, and we'll get to it because things have changed a lot in the last. So
does that mean that the universe that causally affects us we're at the center of it?
No, Well, actually, yes and no. We're always at the center of our own universe, right? I mean, psychologically
Because
and physically.
because of the causality argument that you just laid out, it seems to imply that directly. Because
it certainly does, in the sense that if you want to think of it, and that this is one of the confusions that many of the confusions which I may add to during this podcast, but we'll try not to, is that, when we look out at this thing called the cosmic microwave background radiation, it's a residual radiation left over from the hot Big Bang. And it comes from a sphere, if you wish, that's located with us at the center. Because it early on in the history of the universe, when it was hot and dense, light interacted with matter, and basically it followed a random walk. It wasn't free to travel because all the universe was charged and light would interact and bounce off things. But at a certain point, when the universe was about 300,000 years old, matter became neutral. Protons captured electrons to form hydrogen for the most part. And neutral matter doesn't interact with light as strongly as charged particles. And that meant that radiation, which was kind of trapped early on, when the universe was 300,000 years old, could suddenly travel freely through the universe without really interacting. And when we look out, basically we see space, and the light, can travel and travel and travel. But if we're looking back further in time when we look out, and if we look out in that direction, back to a time when the universe was 300,000 years old, we're kind of sort of going to see a wall, if you wish, because we can't see before that time because the light, couldn't have propagated out, just like it can't propagate out through a wall. Only from the surface of the wall can we see it. And of course, so when I look at the microwave background from Earth, I'm looking, if you wish, at the sphere located almost 13, well, actually it's because of the expansion of the universe, it's about 26 billion light years in each direction because the universe has expanded during the time that the light has been traveling. But don't worry about that complexity. We're looking at a sphere located a certain, let's say 10 to 20 billion light years away from us in all directions, and we literally can't see beyond that. But the sphere we're looking at depends upon where we are, so that if we were doing the same experiment on an intelligent species in another galaxy located 100 million light years away, literally the cosmic microwave background that they would see would be slightly different, because it'd be a sphere centered on a different place. And that's why actually the predictions we can make in some sense as cosmologists are somewhat statistical, because we're talking about a thermal distribution and galaxies and lots of disorder. And so the picture, and we've taken pictures of the microwave background, it's won at least 2 Nobel Prizes for those pictures. The picture that we see has statistical properties which would be identical to those observed by another observer 100 million light years away. But the specifics, the hot spots and the cold spots, would be different, because they'd be looking at a different slice of a statistical distribution.
So that does, correct me if I'm wrong, that does seem to imply that, so the universe is a globe around us, let's say.
Our visible universe.
Our visible universe. Sorry, I want to be precise with my words too. And so I move halfway across the universe and the globe is still there, but now it's shifted that far. And so then I could move another halfway and it would shift again. So this globe moves with the
you.
Observer, so to speak.
Yep.
And that certainly seems to imply that it extends beyond the globe that we see, because if you move, it moves. So, and
exactly. Well, and it wouldn't if there was some edge, but there's no evidence of any edge. Okay. I think that the point is that even before the weirdness of empty space and inflation, it was recognized that the part of the universe we see is unlikely to be everything there is. We're limited in what we can see because of what's seeable, just like being on Earth.
And it's limited because of the speed of light and the age of the universe, but also because of the way the universe was constituted in its early stages.
And the way it's expanded ever since. Let me throw in a wrinkle. If that was clear, now let me muddy it. Okay, because it used to be, again, sensible, even in my early career as a scientist, that we'd assume the older the universe, the longer we live, the older the universe is, the more we'll be able to see, right? Because light can travel further. The universe is expanding, but we thought at the time that expansion was slowing down, and therefore the longer we wait, the more we'll see, because light from further and further objects can get to us. What's really crazy now is because we recognize that apparently empty space is dominating the energy of the universe, that's causing the universe to expand ever faster, faster and faster and faster. And what it means is there are parts of the universe that are literally escaping from our sight. There are parts of the universe that we will never be able to see. And moreover, even more so, there are parts of our universe that we could see now that if we were a civilization that developed 5 billion years from now in real telescopes, that we couldn't see then. Because regions of the universe are eventually moving away from us faster than the speed of light and are now invisible. So the longer we wait, the less we'll see, because more and more galaxies will be literally disappearing behind the horizon the longer we wait. I wrote some papers about that and once a Scientific American article, and I think some of my books, that eventually the far future of the universe, I know we said we'd start out of the past, but the far future is kind of poetic, because up till about 1925, the picture of the universe was quite natural based on observation. One galaxy, we saw one galaxy, the Milky Way galaxy, okay? And beyond that, it was assumed to be eternal, empty, dark space that just was static. And Edwin Hubble, who was famous for discovering the universe was expanding, did something before that. In 1925, he first realized that in fact there were other galaxies, that these things called nebulae in our galaxy with the new 100-inch telescope at Mount Wilson could be discerned and be seen as other island universes. So already that was a revolution in our picture of the universe. Suddenly our galaxy wasn't all there was. There were other galaxies. And then, of course, later on, he discovered the expansion of the universe. The interesting thing is that observers who evolve, and there'll still be stars in, say, even up to 10 trillion years from now, there'll probably still be stars in existence. And you can imagine planets around those stars and intelligent life evolving on those planets. And astronomers would look out from our galaxy. At that time, it'll be a very different looking galaxy because the Andromeda galaxy will have collided with it and all sorts of things will happen. But they'd look out, and the interesting thing is all other galaxies would have disappeared behind the horizon by then. So observers 10 trillion years from now will think they live in the universe we thought we lived in 1925, a universe with one galaxy, and there'll be no evidence that the universe is expanding, no direct evidence, because the galaxies that are now markers that we can measure their motion away from us, they'll have disappeared. And even, it turns out, the cosmic microwave background will have become invisible by that time, which is another bit of evidence for the Big Bang. And while some really smart scientists may come up with some pictures to say, well, really, I can understand what we're seeing if we assume our universe began in a Big Bang, observationally, basically, all the current observational markers of an expanding universe will have disappeared. And poetically, in the far future, they'll think we lived in the mistaken universe we thought we lived in 1925. Because, again, it's kind of interesting. Conventional wisdom in 1925 scientifically was that the universe was static and eternal. And you may know that it was actually a Jesuit priest who was also a physicist who first really suggested the Big Bang. And when it was later shown to be true, for a while the Catholic Church got quite excited because they argued that here was observational evidence that there was a beginning to the universe, as they'd been arguing. It doesn't provide, I would argue, it doesn't provide any such evidence for the universe they discussed. But it was an interesting fact that science, the model was that the universe was more or less static and eternal on large scales, and it was completely wrong. And you might say, and this is where people often write to me, they say, well, how do we know our current model isn't completely wrong? If that we had a Big Bang. And the answer is, then there was no data, basically. And, one of the biggest misconceptions about science and scientific revolutions, in particular revolutions in physics, is the misconception that scientific revolutions do away with everything that went before them. And just like
they're
political...
more like Piagetian revolutions, right?
Yeah, well, in fact, I would argue that even political revolutions never do away with everything that went before them. But in this case, they certainly don't. What survived the test of experiment before that revolution remains completely true. Newton's laws of gravity and motion may have been subsumed in quantum mechanics or relativity, but if I hold a ball up now, it'll fall just as well as described. And I can describe a cannonball. I can even, for the most part, calculate how astronauts are going to go to orbit without needing anything
Yeah, the
beyond Newton.
developmental psychologist Piaget studied Kuhn's scientific revolutions, and his objection essentially was that when a child undergoes a cognitive restructuring, the new structure incorporates all of the knowledge of the old one plus some new knowledge. So it can be revolutionary, but it still subsumes it.
Exactly, and that's exactly what happens in science. So it's not as so we have a lot of data with which we can test ideas, and I'm certain that there's much more we don't know about the universe than we do. What people don't realize is, or don't give credit to, is that there's a lot we do understand. And any new picture, a new understanding will not be able to disagree with the observational evidence that the universe is expanding, that there's a hot cosmic microwave background, all the things we now have discovered that we didn't know about in 1925. And so whatever our picture is of the beginning of time or the end of time in 100 years may be very different, but we know we're not going to ever say that the age of the universe is no longer 13.7 billion years old. That's going to remain true. What happened at the beginning could be completely revolutionarily different. And what happened, if you want to think about it before the beginning, if there even makes sense to describe a before, and it may not make sense because time itself could have originated.
Well, let me ask you about that for a second.
Sure,
okay?
Sure.
Well, I thought a lot about time a long time ago. And it struck me that time is we mark time by change. And so then I thought, well, why not dispense with time as a concept if we mark it by change? Time is average change. If nothing changes, there's no time. So if there's nothing happening, there's no time. There's no before that time. There's an event. And then if there's no event till the next event, there's no duration between those two things if there's only that event and the next event. So, I mean, is there any reason to assume that there's anything about time that is independent of change?
Well, obviously it's a very deep question. And a lot of people spend a lot of time on time. I think far too much time talking about time. In physics, time and space are not different. They're both, if you wish, parameters that simply describe when events happen and where they happen. And that's it. And it turns out that that's the playing field on which the laws of nature play out. The playing field happens to be in space-time. And time is no different than space in principle, except in fact, in practice, time seems very different than space. We can go backwards in space, but it's not clear we can go backwards in time. And that's caused a lot of people, a lot of philosophers and then physicists, a lot of problems and a lot of mental gymnastics. But even, but you could argue that time is a parameter, and I could replace that parameter by some other parameter that is equivalent to time, and you could say that that parameter was change, like the parameter you talk about. And then if there's no change, then you'd say, okay, well you could say that parameter isn't changing, and you call that time.
There's changes happening all the time at the microscopic level, right? I mean, there's an indefinite number of changes, and so statistically, you can extract out an average from that, and you can experience that as duration, and you can define that as time. But if there isn't anything there except one event and then the next event, well, that's it. That there's no time there. There's an event and then there's the next event.
Well, that's where I disagree with you. I guess that's why I refine it, because if nothing is happening, literally if nothing's happening, then time is an irrelevant concept. But so to some extent is space, and to some extent is physics. Because really what we're interested in is describing the process of events, in particular the prediction of events. And that process of going from event to event is parameterized by a useful quantity called time. But if nothing's happening, you're right, it's completely arbitrary, but then we wouldn't be having this conversation because nothing would be happening. So in a universe in which nothing was happening, there would be no time, but there'd be no reason to talk about it either.
All right, so back to the beginning. Now, my understanding, I don't understand why there is something once something is created, because as far as I could tell, and I don't think I was disabused of this notion with the I finished reading The Greatest Story Ever Told so far this week. Why weren't there equal amounts of matter and antimatter produced at the beginning? So they just disappeared. Everything just disappeared.
That's a good question. and we're still
does that have anything to do with uncertainty? With the fact that there isn't, I'm wondering if there wasn't equal numbers produced.
Well, look, the point is that we don't have an answer to that question. And by the way, I think that's really important as a scientist. And too few people, journalists always want answers, and people are always disappointed when they say, we don't know. But I think it's probably one of the most important things that we and parents and teachers should get more used to saying, because it means there's more to discover. And that's wonderful. So the answer is we really don't. It's one of the biggest questions that's really provoked much of the field of research that I've been involved in since I was a student. I remember Steven Weinberg wrote about it when I was a graduate student and got me interested in the whole subject. We now know that we live in a universe that's made of matter. We try and measure antimatter, and there's minuscule amounts of it. And we think most of it's caused by high energy collisions between particles and cosmic rays. As far as we can see, and there are real tests we can do. For a while, people thought maybe we lived in a universe that had equal amounts of matter and antimatter, and they were separated. There were matter regions and antimatter regions, but it turns out there are tests you can do to test that. And all of those tests demonstrate that, as far as we can tell, that that the universe is made of matter, not antimatter. Which again is arbitrary, because of course, if we lived in a universe made of antimatter, we'd call it matter. And and there'd be anti-lovers sitting in anti-cars, making anti-love and all the rest. It wouldn't be different for the most part. But the paradox here is, at early times, the universe is very, very hot. And when it's so hot, one of the central parts of relativity is that energy can turn into matter and matter can turn into energy. So particles of light with enough energy can collide together and produce particles of matter. Okay? But when they do that, if they have enough energy, but since antimatter and matter have exactly the same mass, particles that collide will produce equal amounts of matter and antimatter. If two photons at very high energy, and they don't collide very easily, but if they do, they'll produce particles and antiparticles in equal numbers. Partly because of the conservation of charge, right? The photon doesn't have any charge, and therefore whatever comes out of the collision has to have no charge. So if it produces an electron, it'll have to have a positron, the equal and opposite. So all those interactions, elementary particle interactions, don't really distinguish between matter and antimatter. And therefore, at very early times, if you were a creator, if you were creating a universe and it was very hot and dense, the most reasonable thing would be for it to have equal parts of matter and antimatter. Okay? But somehow, so that's the reasonable assumption for the beginning of time, that the universe had equal amounts of matter and antimatter in a very hot, dense plasma. How do we get to a universe that just has matter? Well, that is the interesting question. And it turns out, by the way, and I know you're interested in what you would call Soviet things, you like the art and everything else, and you and Alexander Solzhenitsyn.
No, I collect it. I don't know if I like it.
Yeah, okay, you collected it.
But I do collect it.
But Andrei Sakharov was a very famous Soviet physicist who's actually probably the father of their hydrogen bomb. But he was also, as you know, won the Nobel Peace Prize because he became a dissident. Interestingly enough, one of his major, in retrospect, one of his major contributions to science was he actually asked in, I think it was 1967, well before any of the physics actually allowed he came up with 3 criteria by which a universe that started out with equal amounts of matter and antimatter could evolve into a universe which just had matter. They're called the Sakharov conditions. And there are 3 of them. One is that you have to depart from thermal equilibrium. Because if you're in thermal equilibrium, everything remains the same. So nothing's going to happen, right? Okay? Thermal equilibrium, like the air in this room.
Okay, so there's a place where uncertainty seems to be relevant, because if the principle of uncertainty holds, you wouldn't have thermal equilibrium. You'd have unavoidable variation.
Well, no, but you have you do have local in thermal equilibrium in this room, there's local variations. The thing about thermal equilibrium is, and you're right. In fact, what you just said there is right. Normally, we talk about thermal equilibrium being a global thing, but we can also talk about microscopic equilibrium, and there are variations. But what happens is that in thermal equilibrium, one particle turns to another particle, big collision, but an equal number of collisions happen in the opposite direction. So there's lots of things happening, but they're all happening in equal opposite ways, so that no global properties are changing. Okay?
Okay.
And certainly the amount of matter in the universe is a global property. Okay. So thermal equilibrium, okay. The second is that you have to have some physical process that tells the difference between particles of matter and antimatter. Okay, because if the physical processes don't tell the difference, then nothing's going to start a situation that has equal numbers and change it to a situation that has unequal numbers. Okay, this property is called it happens to be the laws of physics that tell you matter and antimatter. The laws of physics are the same for matter and antimatter, are related to two symmetries of nature. Something called charge conjugation invariance, which tells you that positive and negative, there's no difference between positive and negative. It's just an arbitrary thing. And it turns out there's no difference between left and right. Okay? If the laws of physics at a microscopic level obey both of those properties, then the laws of physics will not distinguish between matter and antimatter. Only if that's violated, that's called CP, charge and parity. Only if CP is violated can you, by some microscopic physical law, can you evolve from a system with an equal number of particles and antiparticles to one that hasn't. And the third is something called, we call it baryon number non-conservation, but basically matter is made of protons, okay? And electrons are obviously protons and electrons wake up atoms, but electrons are very little mass. Most of the mass in your body is protons and neutrons. They're called baryons, okay? And clearly, if you want to end up with a universe full of protons and neutrons, and more protons and neutrons, if you wish, than antiprotons and antineutrons, then there has to be some process that makes protons when there weren't protons to begin with. So those three, so that's thermal equilibrium, CP and violation of thermal equilibrium, violation of CP invariance, and some process that violates what are called baryon number. Okay? And he wrote those down. And what's amazing is at the time he wrote them down, the laws of physics obeyed thermal equilibrium in the universe, obeyed CP, and obeyed baryon number. So there's no evidence that you could ever do that. And what's been remarkable is that over the last 50 years or so, is as we've studied the microscopic laws of physics, we've discovered both that CP is violated by microscopic laws, and we've discovered processes that could have happened in the early universe that would violate that thermal equilibrium, that nice general, what you call adiabatic expansion of the universe. There could have been abrupt processes during which the universe departed from thermal equilibrium by natural processes that we could describe. In fact, we know there were some of them. We know, if you read my book, we know, for example, now that the two forces of nature, electromagnetism and the weak interaction, that now appear very different, early on in the history of the universe actually represented two different sides of the same coin. They were really part of a single, more unified force. Okay? And the point where the universe cooled down enough so that suddenly electromagnetism began to behave differently than the weak interaction, as the universe cooled down and things suddenly began to behave differently, that's what we call a phase transition. And phase transitions are places where you can depart from thermal equilibrium, right? I don't know if I used the example in the book, but I grew up in Canada, so the example was beer. But if you have a beer party, and you forget to put beer in the refrigerator, you put it in the freezer, and then you forget that you put it in the freezer, and the next day you take it out of the freezer and it's frozen solid. It's not frozen solid; it's still liquid. But you take off the top, and suddenly it freezes instantaneously, and the bottle breaks. That's a phase transition. Because when the beer was being held under high pressure, it wasn't at a low temperature. It wasn't really in thermal equilibrium. When you opened it up, then it could suddenly go into thermal equilibrium, and the preferred state to be in thermal equilibrium was ice. And suddenly, boom, it'd break it. So so phase transitions are points where you can depart from thermal equilibrium momentarily before the transition completes. And
so there's a theoretical explanation for how the antimatter matter.
The point is there's no one theoretical explanation, but we now know all the parts, the Sakharov components exist, but we don't have any good model that puts them all together. We thought we did in the 1980s when I was at Harvard. We thought we we thought there were, even before that, when I was doing my PhD at MIT, we thought there's a model called grand unification. It all looked like it was falling together, and we thought we had the answer to everything, and it turned out the experiments have told us that those pictures are not quite right. There's a host of possible ways of starting out with a universe that has equal amounts of matter and antimatter, and ending up with a universe that has unequal amounts, but we don't know if any of the proposals that we've now made are correct. And if history is any guide, my feeling always is the most likely answer is one we don't yet have. I mean, I've written papers, lots of models that can make that happen, but nature probably isn't smart enough to use any of the models that I've written down, and I suspect it. But so there are lots of ways, but what's neat is that experiments have shown, and that's what's important. It's not just theoretical, mumblings of physicists who like to have nothing better to do. Experiments have shown all the components of the Sakharov requirements for generating matter, a universe that had an asymmetry, are possible in nature and are suggested. I should be a little more careful. We know phase transitions happened in the early universe. We know CP is violated. Baryon number, we don't know to be violated. But all of our models that extend what's called the standard model of particle physics naturally produce at very early times models where baryon number is violated. So it's not implausible. It's certainly not implausible. And so all those things exist. And our current picture is really quite, having said all of that, that's complicated. The current picture that is a little simple, and it's really remarkable. It says that what happened is there were equal amounts of matter and antimatter, and a physical process happened sometime between the Big Bang and the time when the universe was about a millionth of a second old that caused a very slight excess, 1 part in a billion, more particles of matter than antimatter. And that's all you need. You might say, why is that the case? Because we now live in a universe that's just matter. Well, if I have let's say there's 1,000,000,001 particles of matter and a billion particles of antimatter, what will happen as the universe evolves? The particles of matter will annihilate with the particles of antimatter, producing radiation, but there'll be one leftover particle that couldn't find the particle of antimatter to annihilate. So what you'd expect is roughly 1 billion particles of radiation in the universe for every particle of matter. And when we look out, that's exactly what we see. The cosmic microwave background contains roughly 1 billion to 10 billion photons going throughout all of space for every proton in the universe. So in fact, while we think we really live in a universe of matter, what we really live is a universe that's mostly radiation, polluted by a little teeny bit of matter, 1 part in a billion, but that teeny bit of matter is enough to make all of the stars and galaxies in you and I. So one of the things that I'd like to think of in physics is it makes us more and more insignificant as human beings in a cosmic sense. We realize we used to think we're the center of the universe, we're the center of the sun, the sun went around us. It's been a series of these kind of Copernican revolutions where the Earth isn't the center of our solar system, but the sun isn't the center of our galaxy, but our galaxy isn't the center of a cluster of galaxies, and our cluster of galaxies isn't the center of the universe. And now we find that most of the particles in the universe aren't even made of the same stuff as we are. So it pushes us more and more to feeling marginal. And I find that, and a lot of people say, well, that should make us feel sad. But to me, it makes me feel more precious rather than less precious. It's like, obviously, we're getting into the realm of psychology, but my psychological response is, hey, the fact that the universe is accidental as far as I can see and was created without any supernatural shenanigans, the fact that we're cosmically irrelevant, the fact that the universe is going to go on without us, all that doesn't make me feel sad. It makes me feel I should enjoy my brief moment of the sun. I should enjoy my brief, 70 or hopefully more and years. And it makes this accident of life on Earth remarkable that evolution has endowed us with a consciousness so you and I can have these discussions. So I don't find a pointlessness of the universe to be depressing. I find it rather the opposite. And I often, and this may be an area we disagree in, I don't know, but one of the bits of semantics that I've tried to fight is this notion of loss of faith. Like losing your faith is a loss. But to me, losing my faith in those fairy tales, at least, or those incorrect explanations, is not a loss, it's a gain. And using that terminology makes it seem like people always write to me, I now recognize, that I don't believe the Bible stories, but what am I to do? I mean, how can I deal with this loss? And I think they're conditioned to feel like they have a loss. I don't think so. I think you can psychologically create a picture where you don't feel that's a loss. You feel, in fact, you've gained something. And actually, it's the way I feel about many things in life when I'm being well adjusted, which is a small percentage of the time, to be clear. When I have a loss, I often reflect on it afterwards and realize, in fact, how I've gained. That what seemed to be a traumatic experience, or in the end, produced something which is much more valuable. And of course, it's a rationalization, probably, but it allows me to deal with those things anyway. Anyway, that's my little bit of psychology, my little bit of pop psychology for our discussion.
I'm tempted to take it in that direction, but I think I'm going to continue to torture you about the structure of the universe.
I could do that, because one of the things that I hope your listeners will know is that you and I are going to have a podcast on my podcast. I can't wait to have you on my podcast. Maybe we'll be together in the same room, and then I will torture you. Okay. Okay.
That sounds like I'm looking forward to that a lot. Okay. So matter pops into being essentially after things cool down to some degree, and there aren't exactly different laws governing the universe before that, but what would you say, the allowances that the current laws make have a remarkably powerful effect before that.
Yeah, absolutely. The form that the laws of physics do evolve at energy scales, and which laws are important at different energy scales are different. So certain laws of physics, even if they don't change at all, certain things are more important early on, and then other laws become more important later on. Like now, obviously, electromagnetism on small scales is incredibly important. It governs all the biology, all the chemistry, all of the things that we see in the world around us. At early times, it was nuclear physics and particle physics, the laws of the strong and weak interaction, that were determining what was going on. But you're right, eventually, and it took a while, it took a long time before the universe became dominated by matter. Even when the universe was 1 second old and a temperature of about 10 billion degrees, there weren't even elements. That's the other thing that's remarkable. Until the universe was, even protons didn't exist until the universe was somewhere about a millionth of a second old. But elements didn't exist. All of the light elements, hydrogen, helium, and lithium, were, if you wish, created by nuclear reactions in the first 5 minutes of the universe, which is why Steven Weinberg's book called The First 3 Minutes talks about that. So, and those were the only elements created at the beginning of time. Hydrogen. Right,
and they're created from the lightest upward. And that's basically the way that things go across the entire periodic table.
You start with protons. And in fact, it's kind of protons and neutrons, but neutrons are actually unstable, so they decay into protons. It's very fortunate. It turns out, if you want to believe in coincidence, it's just really quite amazing. It's very fortunate that it works out. The neutrons live about 10 minutes. I mean, if I had a neutron here and held it in my hand, in 10 minutes on average, it would decay. Well, you and I have more neutrons in our body than protons. How can that be the case? We've been talking for a lot more than 10 minutes, and I'm sure your listeners are quite aware of that. But the reason is, if you put a neutron in a nucleus, it can become stable. Okay? And it's really quite fortunate that all the neutrons that are more or less, many of the neutrons that are now existing in the universe, got trapped in this form of helium and lithium, because hydrogen just has a proton and electron. Okay? There's a heavy hydrogen, which is deuterium, which is a proton and a neutron electron, and some of that was created in the universe too. But helium has 2 protons and 2 neutrons, and so by helium forming by a series of remarkable nuclear reactions, the universe, if you wish, stored the neutrons that otherwise would have decayed away into protons, and there would be no neutrons left in this universe.
And so they've been stored ever since that time?
For the most part, yeah, they have been, exactly. And so the neutron, and of course, other neutrons have been created in the fiery cores of stars. So what happens is, and I talked about it in the Universe of Nothing in a lecture I gave that sort of was the formation of that book. And I'm not the first person to say that. I know Carl Sagan talked in different ways, but it is really true. What's important for the psychology that you study is carbon, nitrogen, oxygen, phosphorus, iron, all of those things. None of those elements were created in the Big Bang. all of those elements were created much later, literally billions of years later, or hundreds of millions of billions of years later, in the fiery cores of stars where nuclear reactions happen. And that means something that is really, truly the most poetic thing I do know about nature, that every atom in your body, in the first approximation, all the carbon, all the oxygen, was created inside of a star. And that means in order to get into
inside of a star.
And not just forged inside of a star, but in order to get into your body, that star had to explode. So all the atoms in your body, and in fact, probably they've been in many stars, because you probably need many generations. They've experienced the most catastrophic explosion in nature, a supernova. Every atom in your body has experienced that at least once, if not many times. You are a stardust. It sounds,
it's so remarkable that it sounds cliched.
Yeah, exactly. But when I really
it's like a discussion of love.
Yeah, exactly.
It is the case.
But you know what makes it less remarkable for me, as an analogy I gave, is that the atoms in your left hand could have come from a different star than the atoms in your right hand. I just find that amazing. Anyway, it doesn't matter. Whatever turns you on.
So what do you think? Okay, so now we're at the point in the story where atoms are beginning to form, and they're starting with their simple forms, and that's it within the first 3 minutes.
Yeah, first 5 minutes or so.
First 5 minutes. So it's hydrogen first, and then it's helium, and then it's...
Let me even correct you again, because I'll correct me. The nuclei of atoms form. But in fact, there were no atoms until the universe was 300,000 years old, because it was so hot that when atoms exist when protons and neutrons capture electrons, right? Then you get a whole atom. But in the early history of the universe, it was so hot that when an electron got captured, it got knocked out again. So there were only these nuclei, which were charged of protons and electrons, and and it was a plasma of these things. Only when the universe cooled down to about 1,000 degrees or so, maybe 10,000 degrees, somewhere in that region, was the universe cool enough so that protons could capture electrons and neutral hydrogen would form. And those were the first atoms, literally neutral atoms that existed in the universe. And that's when, if you wish, the cosmic microwave background separated from matter, because then once matter became neutral, instead of being a bunch of charged objects, then light and matter kind of decoupled. And that was a momentous period. And that was the first moment that neutral atoms began, when the universe was 300,000
years old. So that's at about 300,000 years.
Yeah. And then not much happened. I mean, and then, from 300,000 years, what happened is the universe cooled and cooled and cooled. And really, it was the dark ages, if you wish, because, there were no stars. It was just matter and radiation, but the radiation
and it's fairly uniformly distributed, and it's expanding and cooling.
Unbelievably uniformly distributed. This was one of the big surprises. Einstein, in order to make a model of the universe, your models are simple. So Einstein and others would make models in which the universe was uniform, because only then could you do the calculations. But then when we look out, we discovered empirically this remarkable fact, which for a long time was quite surprising. And now we have this idea of inflation that in principle explains it. But it's that the universe is uniform across regions that could never have been in causal contact before today. That's really important. The region way over there could not have communicated that region over there before today, but they have the same temperature to 1 part in 100,000. It's remarkable. The universe is unbelievably...
And that's the cosmic background microwave radiation that we're talking about. It's the same in every direction, no matter where you point.
And since matter was coupled to radiation, the more or less distribution of matter is uniform throughout the universe. But now it's not, because you and I are in different places, and distribution of matter.
Well, it sounds like it's another one of those situations where small discontinuities at the beginning were enough to produce very large differences across time.
Exactly, because gravity is attractive. That's the key point. So if you have small lumps anywhere, a little small excess here will begin to grow.
And then that snowballs, so to speak.
And that's exactly the case. There were small, and this is another amazing fact which is not appreciated enough. The small fluctuations in the microwave background we think were due to quantum mechanics.
Yeah, that's where I was thinking about the quantum uncertainty. Yeah. Sorry, it's not the earlier.
We are literally quantum lumps, if you wish. In order to get those...
Because there's quantum discontinuity, uncertainty.
On microscopic scales.
That causes clumping.
Well, eventually...
Or it allows clumping to occur.
Yeah, the point is that we don't see quantum fluctuations on our scales. But remember, the entire observable universe was once inside a region that's the size of an atom. And those scales, quantum fluctuations are very important. And what's amazing is those quantum fluctuations got frozen in into the microwave background characteristics in ways that we can predict and describe. And those quantum fluctuations later formed all the stars and galaxies and everything else because they were lumps. So we really are macroscopic manifestations of quantum mechanics, if you want to think of it that way.
Okay, so let me ask you a question about that quantum fluctuation.
Sure.
So there is uncertainty of location and speed. Yes, I've got that right.
Well, location,
you can measure one, but not the other.
Yeah, there's uncertainty in the combination. But
okay, but that uncertainty is real enough so that in that relatively uniform background, there were actual, let's say, fluctuations. There were discontinuities of position that were sufficient to cause.
There not only were, but they're inevitable. They're required. And
right,
the way that
right.
gets,
but that's an actual phenomenon.
Oh, it's even more. It's more, not only more real and more, but it's also more wild than you just said. That what you just said may not surprise people, but what's even weirder is when you go to the smallest scales. There's another uncertainty principle in quantum mechanics. There's a position and momentum uncertainty, but there's a energy and time uncertainty. And the certainty is if you can measure a system for only a short time, then your ability to measure its energy is very uncertain. So if you can measure it for a longer time, your uncertainty energy goes away. If you measure it for a small time, your uncertainty in energy gets very large, okay? And that means for very short times, empty space can burp out particles and antiparticles. You say, well, that violates the conservation of energy because there was nothing there to begin with. And when I burp out an electron, a positron, suddenly there are particles.
Is that how black holes evaporate?
That is a mechanism by which black holes can be thought of as evaporating, if you want to get there.
Right, because they particles pop up spontaneously. Some of them fall into the black hole.
That's one way of describing Hawking radiation. It's not a bad analogy. It's not a bad. Okay. It's got problems, but it's not a bad analogy. But in real,
I'm glad I'm not completely off the wall here.
No. You're
dabbling around.
No, you're so far you haven't. Except your questions about time, you're right on track. Anyway, so this says that particles can suddenly spontaneously burp out of nothing because as long as they disappear again in a time so short that we can't measure their existence, they don't violate anything. They'd only violate energy conservation if we could measure them. Now that sounds crazy, and it sounds like
sounds something like potential.
Well, it's
to me.
That's right. They have potential to do things, but to be less generous, they sound like talking about how many angels can dance on the head of a pin, right? Because if you can't see them, then what the hell does it matter? The point is we can't see them, but they have indirect effects. That's what's remarkable. So we know that process is happening, not just because physicists like me say it's happening, but because if you take, say, a hydrogen atom, you got a proton and an electron. The laws of quantum mechanics that Dirac developed allow you to calculate the energy levels that electron can have around a proton, and that determines the colors of light that's emitted by hydrogen, right? Okay? We can compare those predictions with observations, and that's one of the bases of knowing that quantum mechanics works, this discrete set of light that's emitted by hydrogen. Well, it works, but it doesn't really work, because it turns out at a gross level it works, but when you try and measure things at the level of 1 part in 1,000 or so, it doesn't work. It turns out the energy levels aren't exactly what you'd think they were. Why is that? That is because the hydrogen atom isn't just a proton electron. It's a proton electron, but in the atom, virtual particles are popping in and out of existence. And say an electron-positron pair pops into existence.
In the atom.
In the atom.
Within the confines of the electron
orbit. Exactly. In that region, well, it's happening everywhere in space, but it's also happening in an atom. But in that region, during the time before that electron-positron pair disappears, the electron in that pair will want to hang around close to the proton, because negative charges are attracted to positive charges, whereas the positron will be kind of repelled. And that'll change the charge distribution inside the atom in a way that we can calculate.
Does that make every atom somewhat unique?
Well, yes and no. Every atom is experiencing the same thing because what's happening is the particles, what's happening again statistically is that all those virtual particles and antiparticles are changing the spectrum of hydrogen, of all hydrogen atoms, by the same amount, because they're happening so fast, they're changing that spectrum in a way that we can calculate. And it is one of the triumphs of theoretical physics that using a theory called quantum electrodynamics developed by Feynman and others and building on what Dirac did, we can calculate to 14 decimal places from first principles what the spectrum of hydrogen should be and how those virtual particles could change that spectrum. And when we compare with observation, it's bang on. There's no other place in science that we can make a theoretical prediction from first principles and compare it to 14 decimal places with observation and get the right answer. So that tells us that those virtual particles that we can't see are really there. Okay? And that means empty space is much more complicated than we had assumed before, which is the reason.
Was that part of what led you to the hypothesis that empty space was? It was. Okay, yeah, so that's all part of the background for that. Exactly. So empty space is a seething pool of virtual particles popping in and out of existence constantly. And so that does sound a lot like potential, like a potential.
And that means not only is it potential, but it can have, but that effect can cause empty space to have energy. In fact, generically, you would expect empty space to have energy. So you might say, what's so surprising? So it's not surprising that empty space has energy. What's surprising, in a sense, is that empty space has so little energy. You might say,
why does it have energy if the particles sum to zero over a short time?
Well, that's a really good point. And the answer is a little more complicated, and it is that. Let me give you an example from quantum mechanics. So if I have what the famous quantum mechanical example of a potential well, I have a little U-shaped well, right? And if I have a ball on that well, it'll roll down the well, but friction will eventually cause it to rest at the bottom, at the lowest energy state, right? It'll lose energy by friction, lowest energy state. It turns out in quantum mechanics, because energy states are quantized, in such a potential well, the lowest energy state is not at the bottom of the potential well. It's a little bit above the bottom. And so the ground state, the lowest energy state that an electron can have trapped in a well, is not at the bottom of the well. It actually has a little bit more energy than the bottom because the energy states are quantized. Classically, the electron...
So that means it can't get to zero?
It can't get to zero. That's a generic property of an electron in a potential well. It's an amazing fact. So that's called the ground state energy in quantum mechanics. And
is there a why to that? I mean, you said it's because it's quantized. I presume that's an explanation, but it's not an explanation I understand.
Okay, let me give you a heuristic explanation that you might like better.
Okay.
You might not like it as much, but it's one that I use in my own mind, so maybe it'll help. Remember, we tell us in quantum mechanics, particles are also waves, right? So the electron has a wavelength, okay? I don't know if you play music. Do you play music at all?
Badly.
Me too, very badly, but I like to play. Okay, so when I hit a piano key, I hear a note. Why? Because that string has a certain length, and there are vibrations that can be on that string, but the only vibrations that persist are ones that have a very specific relationship with their wavelength to the length of that string. That's called resonance, right? So, and that's why, because the wave goes along the string, it comes back, then it bounces back and comes along and reinforces. But only when the wavelength in that case is exactly equal to the length of the string will you have resonance. Will the string be able to persist? Okay, now, electron has a wavelength. And the way to think about a stationary state of an electron is it's like a resonant note in a musical instrument. So I have a potential well, and the electron can only exist at those distances where its wavelength is an exact relationship to the width of the potential well.
So is it reasonable to say that I mean, an electron can't exist and have zero energy? That's not possible.
Let me think if that's a good. If it were, the only way it could is if its wavelength were infinitely big. Because it turns out the wavelength of an electron is related to its total energy, inversely related. So if you want to think about this, an electron that's at rest, if you want to think about it, would have a wavelength that what's called the Broglie wavelength, which is infinitely big in size. So only in an infinitely big universe can an electron really have a ground state energy that's exactly zero.
All right. Now, I'm going to ask one more question about this, then I'm going to shut up about this. Is that also uncertainty issue? Is because
Yes.
if it's at zero, you can specify it exactly. So then it has to have an infinitely large wavelength.
Yeah,
That's the reason.
That's basically the answer, so more or less. Yeah. Its position, if you more or less, if it's at rest, its momentum is exactly zero.
Right, and you can exactly specify
and therefore you
that.
don't know where its position is, and therefore its position is equally likely anywhere in the universe. So only, yeah. So
Okay.
Yeah, I know it's crazy. It's crazy.
Yeah, well, these are more like they're like concurrent, incomprehensible descriptions rather than explanations.
Well, yeah, except the theory. That's when
you can actually predict, obviously,
and it works. But
right.
I mean, but there's something you've hit on which is really important. A lot of people get hung up on the interpretation of quantum mechanics, and people write books about it in many worlds. And they, lately there's somebody who wrote a book and tried to sell books. But the point is that it's nice to talk about all that, but it's really irrelevant because as actually a brilliant, I first realized it due to a colleague of mine at Harvard who was really the smartest person there in the physics department. He's now dead, Sidney Coleman. He said the proper thing to talk about is not the interpretation of quantum mechanics. It's the interpretation of classical mechanics. Because the real world is quantum mechanical. And any classical picture we impose on it is going to be crazy. But you don't have to think of them as real. They're all just different approximations to a reality, an underlying reality, which can't be described by any classical picture. So that's why all these classical pictures seem crazy, because none of them is complete.
Well, if you look at this psychologically, I'm going to refer to Piaget again. I mean, Piaget pointed out that we derive our concepts from our practical manipulations of things. So, for example, you might ask why is this one thing? I could say, well, it's five things.
Yeah. Okay.
Well, the question is, well, what's a thing?
Yeah.
Well, look, it moves as a unit. Therefore, it's a thing. So that's one. Well, it could be five if I broke it apart. Now it's two.
Yeah.
But the concept itself is predicated on our interactions at this scale. And so we're going to derive our sense of reality from our practical interactions at this scale. And your claim, the claim of the quantum mechanics in general, is that doesn't apply at the micro scale. So our intuitions are gone because our intuitions are predicated on our embodiment at this level of analysis.
Absolutely. In fact, the purpose of The Greatest Story Ever Told So Far, that particular book, is to say something remarkable. The world of our experience is an illusion. Now, I know I hate to say it because it breeds all sorts of mumbo jumbo and people start doing, but at a fundamental scale, at the smallest scales, everything that defines our universe, including matter and mass, really the things that make the universe we experience, are really accidents of our circumstances rather than fundamental properties of the universe. So our universe.
Yeah, well, that's something I would like, and we can do this again when we talk again, because I'm always curious about that leap into purposelessness. And one of the things I would like to ask you just briefly on that subject is, as the universe cools, we do see a gradual increase in at least one sort of important complexity, right? And that's the building of let's say the building of the periodic table. And so atoms become more and more complex and sophisticated as the universe cools. That seems like a kind of directionality that's built into the structure itself. And it isn't, I mean, do you think that's is that necessarily discontinuous with the radical increase in complexity that you start to see 3.5 billion years ago when life emerges? Or is that the same process of complexification?
Well, okay, it's a good question. And the answer is it's all momentary. It's a momentary accident. It is true that the stars, as individual stars evolve, they build up heavier and heavier elements. Okay, they do it at the expense of their surroundings by increasing the disorder in their surroundings. Right, they're emitting energy.
Right.
Okay, so there's no violation.
There's localized increase in complexity, like us.
Yeah, but it's all momentary. If you follow it long enough, the heavy elements are going to disappear. Matter is going to disappear, and the long term, the universe will just be pure radiation again. So this buildup of complexity, which you're absolutely sure is not a direction of the universe. It's a momentary but fortunate imbalance that will exist for a while until the universe catches up with it. And
that's a real problem in discussing concepts, isn't it? Because you can take a time scale and change the time scale, and all of a sudden the phenomena changes completely. That's what people do to themselves often when they think about the meaninglessness of their life. It's like, well, wait a second, I could make the case, and I've made this with my clients approximately, is if you're thinking on a time scale that makes your life irrelevant, that's the wrong time scale for the problem. That's the hopelessness is an indication that you're using the wrong frame.
Absolutely.
And you'd say, well, what's the proof of that? And I would say, well, the hopelessness is the proof of that. Now, you might not regard that as proof, but it's a point that's at least worth considering, because you could say, well, what good is a Beethoven symphony across a span of 1 trillion years? It's like, well, none, but why? What good is posing that question?
Yeah, well, exactly. Well, I couldn't agree with you more. The fact that we have, there's no obvious purpose to the universe, the fact that we and everything we've created will long be gone, that can depress you. But the opposite side of the coin, it seems to me, if I were a clinician, that I would try to argue to my clients, is that it makes every moment of that accident of your own existence special. And every instant is more special because it's finite, because it's so unique. And therefore, you're right, there may be no cosmic purpose to your existence, but you create your own purpose. I know you write about meaning, you wrote a whole book about meaning, but I would argue there's no objective meaning to the universe. We make our own meaning. And to the extent we make our own meaning, our lives are more or less valuable to us and to others around us. And so I would
I would quibble with that. And maybe it's not just a quibble, because I don't think meaning is something we create. I think it's something that manifests itself to us. Now, look, I know it's not that simple, because we do make decisions, but it's very frequently the case. And you know this as a scientist. For example, you may have a moment of insight into some phenomena. So that's deeply meaningful. But it isn't so much that is something you create, although you can seek it out. It's more like that's something that bursts on you.
Yeah. Okay. Well, it'll be an interesting question to see if we're debating semantics here or not.
Right.
I guess at a fundamental scale, and maybe we can follow this up in when we talk in my podcast, but I tend not to think that there's an objective meaning to the universe. There's existence.
Well, it may be that objective and meaning aren't well suited for one another, right? Because you could also make the case that the objective viewpoint precludes meaning as part of its operation. Yeah. And I think you can make a strong case that the scientific method is designed to exclude subjective meaning. That's actually one of its remarkable strengths, but it has a cost. The cost is, well, what do you do with the phenomena of meaning? Well, it doesn't exist scientifically. Well, that is something we could talk about for a long time, because that'll pull us into the question of whether what's conceptualized as objective reality is a sufficiently sophisticated conception of reality itself. And it isn't obvious to me that it is, because it does have this tendency to exclude the subjective by its method.
Okay, that's good, because I would say for me it's perfectly fine. The fact that it excludes the subjective is its strength, not its weakness, in my opinion.
Well, it is one of its strengths. There's no doubt about that, because because by excluding the subjective, you can discover what's transpersonally universal. Mm-hmm. But that also may mean that there are things you exclude that are real, that are necessary.
I used to read. Well, I like Oliver Sacks, so I used to read a lot. And one of his last books before he died was on hallucinations. And one of the things that really, at the beginning of his book, that really hit me, and it was relevant to something I was working on at the time, and I honestly forget it, but is his point that to people who are experiencing hallucinations, they're real. Well, that's the thing about real. Real is there is objectively real. Let's make no mistake about that. And objectively real is powerful, but it isn't obvious to me that objective and real are synonymous. Well, when it comes to our own psyche, I couldn't agree with you more, which is why I tell people, by the way, when I was a kid, I wanted to be if neither of my parents went to university, so I didn't know the term neuroscience, so I wanted to be a brain surgeon. My mother wanted me to be a doctor, a nice Jewish boy, and I wanted to be, and what interested me most was the brain, and I thought, well, neurosurgery must be the way to do it. I didn't realize it wasn't. But one of the reasons I do physics is it's so much damn easier. It's just so much easier than psychology or neuroscience. It's because because of these complexities of psyche. And so I do go back to this reason is a slave of passion. I mean, the fact that our whole understanding of our own existence is not really based on reason. I try as a scientist
Well,
to do
it's
it.
certainly not based on our capacity to what would you say, to conceptualize objective reality. That isn't how people think. Christ,
Or
we've
work
only
or
thought
act.
like that for 500 years.
Yeah,
It's really powerful, but it's not the way we naturally, and that's also something
true
that's
for
greatly
scientists.
mysterious to me.
Well, but that's what's so wonderful about science to me is the recognition that scientists are people, which is a secret that most people don't realize, and therefore they're subject to all of the whims and slings and arrows of fortune, and so the scientific method is developed to realize that scientists are bound to make mistakes and be human, and the scientific method is to catch those mistakes. I argued recently, in fact, at Oxford Union, and they didn't get the point because they're all woke, but the students, but there were, there was a debate
That's terrible. That's a terrible thing.
I know,
if that's
but
the case, it's so terrible.
You'll be surprised. There was a debate on, the question was, we are all religious. And I asked to speak on the pro side. My colleagues, my atheist colleagues, people were on the anti side, and they were shocked that I wanted to speak on the pro side. And my argument was quite simple. If we weren't all religious, we wouldn't need science. If we didn't all want to believe.
Right. That's exactly right, man. That's exactly right.
Okay, so we agree. I mean, they didn't get the point. And I would argue.
Yeah, well, that was part of what I was trying to point out to Sam Harris is that, and this is something I learned at least in part from reading Jung. Like his claim was that alchemy, the ideas of alchemy grew out of a religious foundation, and then science emerged out of alchemy.
Yeah.
It's like it's nested. Science is nested inside an alchemical fantasy that's nested inside a religious fantasy.
Well, I wouldn't say nested. I would say it grew out of it. Like I was born from my mother and father who, and I like to think that that a lot of who I am is that, but I grew out of it.
Here's why I think it has to be nested still.
Okay.
Now, and this is something we could talk about a lot. The objects that draw a scientist's attention aren't determined by scientific processes. The fantasy, you see what I mean, is that you get interested in some things and you pursue those. Now that's informed by your scientific knowledge, but so Jung's point, for example, was that science was a materialist redemptive myth that grew up as a counterposition to the spiritualist redemptive myth, right? So you imagine there was an idea, which was that we could redeem our inadequacy through spiritual discipline. Okay, we tried that for a long time. It wasn't enough. People were still suffering from leprosy. Yeah. Okay, so there's a fantasy emerges over thousands of years. Maybe we should investigate the transformations of matter. There's redemptive information residing in the transformations of matter. We could investigate that, and that would make life better. And so the motivational goal behind science is the expansion of human competence. And that's not a scientific goal. That's a motivational goal.
Yeah, I agree with you. But where I guess that we disagree, and we could have this discussion, is that I think you're right. And that's what I said before. Scientists are people. So they're motivated by they're motivated by greed, by fame, by jealousy, as well as by facts.
By awe
and wonder. I mean, I wanted to point out, I mean, we're all, that's why I'm a scientist. I'm demonstrating about awe and wonder and fascination. But I'm also, the questions I ask are partly determined by the time in which I live. But I don't want to be postmodern, because the point is that what's great, so that's all true from a psychological perspective. So you may say that the motivations of science are kind of a personal fantasy. But what's great is the science overcomes that, so that you're right. In fact, in my book, in the book you read, The Greatest Story Ever Told So Far, I make a big point of saying scientists were all moving in this direction, and it was the wrong direction.
It doesn't overcome the motivation. It doesn't overcome the motivation. It overcomes the contamination of the theory by the motivational impulse.
But the motivation changes because the results force it upon you. Scientists are forced, kicking and screaming, to change their minds. They don't want to. But that motivation of the kind of questions you ask and that's the greatness of science, because it's empirical, because it's not based on just what I want, but what nature tells me is the case. And so eventually, all the scientists who want this, and no doubt were driven in that direction because they wanted that, find out that one is wrong and they have to go over here. And that's the beauty of science. It's that nature determines what's beautiful ultimately. There was a while when string theorists talked about the elegant universe and all that. Elegant and beauty don't matter. Nature determines it, not scientists. And eventually we get drawn until we eventually come to a picture where we think it's beautiful. But it was nature, something that was incredibly ugly in the beginning that we thought was ugly ends up being beautiful because we force our picture to understand that that's the way it really is. And then we develop an understanding of it. But so that's the beauty. It's that I guess I don't think of it as a fantasy in that sense. Maybe the motivation is fantastical. And even the process at some level.
Well, there's a proposition, right? Which I think look, let me give you another example of this and you tell me what you think.
Okay.
Okay. So, I'll try to formulate this properly. Although I may not be able to do it. We have a hypothesis that's a fantasy, I would say, that the increase of knowledge through technical means will be of benefit to us as individuals and as a species. Okay, that is a fantasy. Now, it may be accurate. It's the fantasy that we've staked ourselves on, but it's not provable. And we're actually ambivalent about it because we generate apocalyptic nightmares all the time. And we know that our technological prowess has a Frankenstein element. Sure. So it's not like we're 100% convinced that this nonstop onslaught of knowledge generation is necessarily in our best interests. And you could also make a case, an evolutionary case, that most species are stunningly conservative. If something works, man, they do not deviate from it.
Sure.
Whereas we're just transforming like mad. And so we do have this fantasy, which is we can escape our static destiny by the acquisition of knowledge, by going out into the unknown. That's Star Trek, right? Yeah. You wrote books on the physics of Star Trek, to go boldly where no one has gone before. Yeah. And that will be of net benefit to us. And that's the fantasy within which this is nested. And I don't think that does change. Well, I understand your point. Within that, there's transformations constantly.
I think it wouldn't. Well, look, I agree with you to the most part. And in fact, regarding the apocalyptic things, one of the things you didn't mention is that I was chairman of the board of sponsors of the Bulletin of the Atomic Scientist for a dozen years that sets the doomsday clock. So every year I'd have to stare apocalypse right in the face. But I think the reason that fantasy has persisted, I would argue, is that it, like many fantasies, is that it has an evolutionary success. And the reason
I agree,
and the reason that it persists is that we have found that when we developed antibiotics, we can live longer. I mean, so there's a hope, and you're right. And it comes back to what I said before. Reason is a slave of passion. I recognize that when I think I'm being driven by pure rationality, I have to recognize that there's passion behind it.
Well, that's it. This is so okay. And I think part of that, again, this is something I tried to draw out in my conversations with Harris is, well, we are evolved biological creatures. We're motivationally driven. We have a pattern. We are not rational. That's wrong. Now we can learn to be rational with great difficulty.
Yeah.
But fundamentally, and maybe that's a tool, but there is underneath this, you said it was an instinct. So we could take that apart a little bit. Yeah. So the prefrontal cortex grew out of the motor cortex. Mm-hmm. So the motor cortex enables you to engage in voluntary activity. Yeah. The prefrontal cortex enables you to abstractly represent motor activity, play it out in an avatar-like universe, and kill off stupid ideas before they kill you. So we've evolved to produce hypotheses, test them through dialectic often, and dispense with those that don't work. And so we've staked ourselves on that attempt, and we've evolved to be able to do that. And science, I believe, is the extension of that, the practical extension of that.
The most successful extension, I would argue.
Yes, it's so successful so far, right?
Yeah, so far.
We have the time frame problem.
Yeah, exactly.
So on the apocalyptic end, let me ask you what you think of this. So we have a particular view of a hydrogen atom. Mm-hmm. Now, it's very reductionistic, right? And you can see the power of that because we understand hydrogen atoms well enough to turn them into bombs.
Yeah.
But you could also argue that it's because of that it's because of the limitations of that form of knowledge that we were inclined to turn them into bombs, that we separated the hydrogen atom from its context, its broad context. It enabled us to manipulate a tiny fragment of reality to exclude the rest of reality from that consideration. That bestowed upon us a tremendous power, but look what it produced. It produced the hydrogen bomb. And, that could be evidence that the theory, however practically useful for producing deadly machinery, was not useful at all at a larger scale of analysis. And that's the paradox, I guess, of the reductionistic approach.
Yeah, I think it's kind of like, reminds me of the Sorcerer's Apprentice, a movie with Mickey Mouse or whatever it was, I think
Mickey Mouse. Yeah.
And is the sense that it is a remarkable, or maybe I should do Spider-Man: with great power comes great responsibility, but which may be a summary of your book. But anyway, we have this weird, I can't agree with you more. We have this weird dichotomy. We've discovered science. The scientific method was a discovery. It took a while to discover it. When the Greeks didn't have it, they did a lot, but if they'd been able to know about empirical evidence, they would have done a lot more. And so it was a discovery, and it's a discovery that was incredibly powerful, that it works. But we humans, didn't evolve to discover the scientific method. I mean, we had the capability, and therefore we have all sorts of evolutionary baggage that makes us human. And so we're, on the one hand, have this incredible power by using the scientific method, but on the other hand, have the fact that we are human, and we have all the slings and arrows that came with being human, all of the evolutionarily positive and negative features of having developed a psyche as you described it. One with, I had a podcast with Joseph Ledoux. I don't know if you know him.
Yeah.
We talked a great deal about fear in the amygdala and how those things play out. But so we have the people that are manipulating this scientific method who are subject to all of the concerns that may, the jealousies, the insecurities, and the wonder all combined. And somehow we have to combine those to keep us safe and secure, and to make in principle a better, again, just saying we want a better future for our children. You're right. That's a fantasy too. That's a claim. It doesn't have to be. Why do we want to do that? Well, for some reason we think it's a good idea. Maybe
for some reason we believe that there's such thing as better.
Yeah.
Right?
And we quantify it, and again, I would argue, see, to me, I'm a solid empiricist. If there's not an empirical way of defining why it's better, then it's an irrelevant concept. And that's why I'm a very pedestrian kind of guy. If you can't measure it, don't talk about it to some extent.
Right.
And so,
if you can't measure it, you can't define it, and then it's hard to tell what the hell you're talking about.
Then it just ends up being semantics. Then it ends up being pure intellectual masturbation, which is a lot of.
Yeah, and you can shift the concept around at your convenience, which is not helpful.
And that's what sort of, I would argue, much of postmodernism is all about. Is that it's lost track of what is real. And it's just sort of intellectual circles.
All right. So there's other questions about physics I would like to ask you, but I'm not going to, because we're running out of time, unfortunately. But I will ask you something. I'll ask you something instead that comes out of what we've just been discussing. So you just went on this panel at Oxford, you said, was it Oxford?
It was the Oxford Union debate. Yeah.
Okay. Yeah. So, and I know you're also interested in social transformations and what's happening in the universities. And you described the crowd at Oxford as woke. So I'm going to tell you something I've been thinking about. I'd like you to tell me what you think about it.
Oh, sure.
So, I was thinking for a long time about the advantages of a democratic monarchy, like Great Britain. Okay, so imagine instead of executive, legislative, and judicial, there's 4 branches of government.
Okay.
Legislative, judicial, executive, and symbolic. Okay, and so it's helpful to have the Queen, because then the president isn't the Queen, or the president isn't the king.
That's the great thing about a constitutional monarchy. You and I both have lived in Canada and the United States, and I agree.
Okay, so you can so you might say that in a place where there is no 4th branch of government, the president, the executive, tends to take on the symbolic weight of the king.
Yeah.
Okay, we agree on that. That's possible, anyways.
Absolutely.
Okay,
I think it's one of the problems of American politics. Yeah.
Okay, and now I would say that's also related to the problem of the separation of church and state. And one of the things the West seems to have got right is the idea that we should render unto Caesar what is Caesar's and render unto God what is God's.
Well,
it's an analogous idea. That's okay. You don't. I'll just continue where I'm going.
I need that to be described more, but okay, yeah.
Yeah. Well, imagine there's a practical necessity for the separation of the religious impulse from the political impulse. But imagine that there's a psychological necessity for that too.
Okay.
And that if there aren't domains specified out for the different domains of practical thought, political, economic, religious, then they contaminate each other. And what happens is you don't get rid of the religion. You contaminate the politics with it.
Mm-hmm. Okay.
And so now I've been watching what's been happening to Richard Dawkins, for example.
Yeah.
Right. And now Richard's idea, and I'm an admirer of Dawkins. He can think, I mean, he's brilliant. And I've read his books. I understand what he's doing and why. And I get his argument. I think it's incomplete for reasons we could get into and probably will. But I think there's something missing there. And then it's playing out is that when you remove the religious sphere and you confuse it with superstition, or you fail to discriminate between the valid elements of it and the superstitious elements, you don't get rid of the religious impulse. It goes somewhere else. Oh, yeah. And I think
if you're saying it's going into secular religiosity now,
well, what do you think?
I agree.
I mean, what does it look like to you?
No, I said that I've written on it, and that was my argument. Is that we're seeing many of the aspects of religion being manifest in secular arguments, as someone pointed out. The only difference being, unlike at least the Christian religion, there's no possibility of absolution, which is
but that's not funny.
Yeah, I know,
right?
it's
That's
not funny.
Seriously not funny.
I know.
But I agree with you.
I know it's serious and not funny. Believe me, I know it very well.
I know you do. I know, but that also points out what a remarkable achievement the idea of absolution is, because it's like the presumption of innocence. Those two things those are miraculous.
Yeah, well, I agree.
Constructs of thought.
I agree, and I'm glad we're having this discussion. One of the when you talked about the symbolic, one of the problems I sometimes have with you from having read you in the past, and we'll talk about this, is as you say things and I don't really understand what they mean. I mean, they're sufficiently vague. I find them vague enough that I really want them to know how you're defining things, and I've really enjoyed the fact that you've been defining things. And I think so I would agree with you completely. We have to realize, and I've had this discussion, as you probably know, Richard and I have had discussions on a lot. There's a movie about us called The Unbelievers, and we spent a lot of time together. And I think our views have come together in different ways. I would argue that religion on the whole has not been a good thing for people. Okay, that's the first argument. But we shouldn't realize, we have to realize that in order that it does serve an evolutionary purpose, if you want to call it purpose, it's there because it has survived all of societies because it meets some human needs in one way or another. And therefore we have to ask, what needs does it satisfy? And realize what they are, and how can we provide them without the fairy tales? So I guess
we definitely do have to ask that question in an extraordinarily serious. One of the things that we might want to do, if we can figure out how to do it, is also to have a discussion with Roland Griffith.
Okay.
Do you know Roland Griffith's work?
Not as well as you, obviously.
Okay, well, he's been investigating psychedelics with psilocybin.
Yeah,
and he's a very solid scientist.
Yeah, I've heard people talk about yeah. Okay.
Yeah. Well, there's a mystery there that's virtually unfathomable, and Griffiths is a very, very solid scientist, and that's another place that would make an interesting. But it's relevant to this point because there are. I think the reason that there has to be a religious domain is because religious questions will never go away. Well, and so even if you get rid of the answers, you can't get rid of the questions.
But you never want to get rid of the questions. I would argue that is that's my big argument about everything, is that we have to encourage questioning. In fact, that's what education should be based on. It should be based on answers. It should be based on questions. So I don't think I have no desire to get rid of those questions. Like, why, if you want to call it, why are we here? Or why do, yes. I would argue the why questions ultimately, however, the difference may be, and I know Richard has gotten involved in this too, because he wrote the foreword for one of my books, but the why questions are really all how questions. they only remain why questions if you believe there's some fundamental purpose. And since there's no evidence of that, ultimately, when you ask why are we here, it really means how are we here. When you ask why does your heart pump blood, it doesn't mean that there's someone made up. It means what are the biochemical processes by which your heart allows your body to exist.
All right. So let me respond to that a bit. And I understand your point and take it very seriously. And so, but what I've been looking at, because I do look at this biologically to begin with, because I try to look at things scientifically insofar as the science allows those things to be viewed.
Okay. Well,
and so to the degree that I can look at religious matters from a biological perspective, I do that because it's simpler. Okay. So I believe that the religious instinct manifests itself in a variety of fundamental motivations, but they're abstract motivations to some degree. So the experience of awe, that's a major one. The experience of beauty, that's another one. The experience of admiration and the desire to imitate, those are crucial. And so one of the things that I would point out, you can tell me what you think about this, and I've been trying to formalize this idea, and I don't know its extent. So I look at Christianity in particular, although not uniquely Christianity, but Christianity in particular, as a thousands of years investigation into the structure of the abstracted ideal to imitate. So imagine we imitate those we admire. Okay, but we're abstract creatures, so we want to know what's the essence of what should be imitated itself. Now, we investigate that. It's not all explicit. We have to represent it in music. We have to represent it in art. We have to represent it in architecture, because we're hitting at it from multiple different domains. And that is a reductionistic argument, right? It says nothing to do about divinity itself.
Sure.
It's purely psychological or biological argument.
Well, where I would disagree with you, and I like the way you've described it in many ways, but where I disagree with you, I guess, would be the word investigation. My problem with Christianity, and I've said this, I've debated once at Yale many years ago the theology, and I've argued that, and I've argued with theologians. I've said, give me an example in the last 400 years of a contribution of theology to knowledge. And you know what they all say? What do you mean by knowledge? Now, if you ask
what do you mean by theology?
Well, okay, maybe, but I would argue
because I would point to Nietzsche and Jung.
Yeah, okay, but I would say if you asked a psychologist or a chemist or a biologist what contributions and all, they'd list these things. But the point is that my problem with Christianity is it stopped asking questions. It stopped being an investigation, and it was a dictum. Here's the answer. Yes. Don't ask any more questions, and that is the antithesis of what I exist for. So I think that's probably
look. Factor analytic studies of religion reveal something like two factors. There's a dogmatic element, and there's a spiritual element. And if you do large-scale surveys of people now, you see that their faith in the dogmatic element has declined substantially, but their spiritual claims have not.
But again, I'd ask you, I don't know whenever someone uses the word spiritual, for me, my mind kind of glazes over because I have no idea what they're talking about.
Well, no, I think it's on the investigative side. That's why I brought that up. Because I think what you're objecting to, correct me again if I'm wrong, but it's the same thing that you object to as a scientist. You object to dogma as de facto dogma.
Absolutely. Okay, but everything is up subject to question. Nothing is sacred.
Right. So that's the continued investigation of the creative mind.
Yeah.
So now, but that can't be quite right either, though, because when you move forward, you always move forward on the basis of dogma, but you question it. Like you do both at the same time, which is what you said people should be doing at the beginning, because you do assume the validity of your knowledge to move forward until you hit an impediment, and then you question it.
You have to make assumptions to move forward. The difference between science and religion is you can recognize later that those assumptions are wrong. And that's the beauty. That's what, to me, the distinction between science and religion. We all make assumptions. And in fact, I love the term I've often quoted from the X-Files where Fox Mulder says, I want to believe. We all want to believe. As a scientist, I want to believe. That's why we're all religious, I argued, in that sense. We all want to believe. The difference is science eventually has a technique allows us to say, yeah, but that belief was wrong. And that's the beauty. That's why I like science. It works in that sense. But we all have to make some hypothesis, but the willingness to dispense with it, even if it's central to our being. And that's what I say to everyone. If an education for everyone should be, if it's at its best, should comprise one thing, that at some point you find that something that's central to your being, something you feel that's central to your existence, you find out to be wrong. Because that is the liberation that education should provide. And that's part of my problem
also
with
humility, isn't it?
Yeah, and that's part of my problem with the getting back to the
dogma.
wokeness, is that people aren't allowed to ask questions because and that's the antithesis of knowledge. Anyway.
So is that the antithesis as well of the true religious impulse? Is to question and search, because you don't look. Israel means those who struggle with God, right?
Yeah,
it doesn't mean those who have got God right.
Well, yeah, no, I mean, one of the reasons, but it's, again, I recognize that part of the reason I feel this way is because I wasn't brought up in a religious family, but I was still brought up in a Jewish family. So it's natural to say, hey, there's nice things about the Jewish religion. And one of the things that I like about the Jewish religion is, yeah, you can question God and all of that. But that doesn't make me think that, but at the same time, it's all still based on a ridiculous fallacy that doesn't make it any more legitimate. Culturally, I like the cultural. It's like genes, okay? I like the expression, the cultural expression, but the underlying basis of Judaism is just as ridiculous. In fact, just as ridiculous, as evil, as vicious as Christianity and Islam and most other religions. So I guess I like the cultural manifestation. So yeah, there are lots of cultural Jews, but I don't even say that. I don't find myself as, people say, why don't you define yourself as Jewish now? And it's because, well, it doesn't mean anything to me. I mean, maybe from the fact that I was brought up in a certain way, but I try not to identify myself by, whether I'm Canadian or American. Those things aren't as important to me as what I'm thinking. And yeah, I don't think
it does strike me that you are someone who's part of Israel in terms of the struggle.
Oh, sure. Yeah.
I mean, it blew me away when I found out that was what that word meant. It really shocked me to my depths.
Yeah. Well, it does surprise me.
It's associated with the struggle.
But I don't think you should sometimes I think you tend to, it's a nice discovery, but don't read into it more than it is. I mean, after all, the Yahweh was a word that you weren't allowed to say. I mean, it's based at the same time as being based on questioning. It's also based on absolutes that you're not allowed to disobey. And therefore it is evil in the sense that every other religion is evil, because there shouldn't be questions you can't ask. There shouldn't be words you can't use, whether it's Yahweh or ginger.
Look, we should probably leave the rest of this, I would say, because we had a good discussion.
Oh, we did.
And it's a really good place to end.
It is a good place to end. And we began, and I look forward to following this. It's really been a true pleasure, really. And I hope
me as well
will have found something in our 2 hours of discussion, if it's a science or otherwise, to see that there's a lot more left to discuss. And I look forward not just to my podcast, but having more chance maybe to discuss publicly too. It's been a real pleasure, and
great. I really enjoyed it, and thank you very much. Thank you very much. I have many more questions for you, but they'll wait. Yeah. All right. Great. I'm looking forward to when we meet again.
Good. Well, it would be
thanks a lot.
It would be bad if in 2 hours we got through everything.
Yes. Yes, that wouldn't be so good.
Okay.
All right.
Okay.